Guys, Mr. Hedrick back here with you in a new unit on exponents and logarithms. It's a continuation of our last unit actually, and whereas our last unit focused more on graphing and key features and transformations, in this unit we're going to focus more on things like solving, real world problems, and inverses, and that's actually what we're going to talk about today. But we're going to start by learning a new method to evaluate or calculate logarithms that we didn't see in our last unit. This is going to be called the change of base formula. If you remember in our last unit, one of our points was that Desmos, that calculator, doesn't like it when you try to type in a logarithm with a very specific base like 4, for example. What we're going to learn today, called the change of base formula, will allow you to continue to use Desmos in their calculator by changing the base of your logarithm. So we're going to see what that looks like. The formula is given as follows. So if you have a logarithm with a specific base and then some number, what you can do to be able to calculate that logarithm is to take the log of A on top of a division problem, log of B base, B bottom, on the division problem. So what this does is it changes your base. Really what you have here is an invisible 10. Desmos and every other calculator really has that as the default base, which is why it really only works with a 10 rather than something like a 4. But if you ever do start with a different base than 10, okay, an invisible 10, you can change the base with a change of base formula as follows. You can take the log of A over the log of whatever base that you have, and the invisible base will now be a 10. You've changed your base. The calculator should now be able to tell you what answer you should get from whatever logarithm you had. And an example that might clarify things here would be if we have log base 2 of 32, okay, if you try to type this into Desmos, it won't give you an answer. But what you can do is take the log of 32 on top divided by the log of your base 2 on bottom, and it will actually give you an answer. That answer will be a 5, and that's because, once again, you have changed your base. You really have an invisible 10 here and here, okay? And the calculator works well with that. Okay? So all you've done is change your base, use the change of base formula. Base B, whatever that base is, it goes on the bottom of your logarithm division problem. Whatever other number you have, take the log of that on top. So one more example like this. We can see up top here, we have a 3 and then this exponent. And that exponent is a logarithm. So what we're going to want to do is try to calculate or evaluate this first. What is that? Okay. Remember, you can take, so 3 is the base, 3 stays the base. You can take the base 4, base B, bottom B of a logarithm division problem. This changes your base. Okay. Try and type this in your calculator. Try to type whatever's in parentheses there, log of 64 over log of 4. Type that into the Desmos calculator. It should simplify your exponent to be 3. Okay. Simplifies things to be a 3. It used your change of base formula. You now have an invisible 10 as your base. The calculator likes that. And then 3 to the power of 3. That's not 3 times 3. It's 3 to the third power. 3 times 3 times 3 will be 27. That'll be your final answer there. We did need to use the change of base formula at the beginning. Once we did, that allowed us to simplify our exponent and then take 3 to that power. So that's your change of base formula. One more thing I want to talk about today is inverses. So first we're going to talk about what those mean and then how you can find the inverse to a function that you're given. Okay. Remember that inverses are like opposites, okay, or In this case, you're switching x and y. We talked about this in our last semester, actually. I believe that was with rational functions. But just like logarithms and exponents are opposites, and addition and subtraction are opposites, when you're looking for a inverse of a function, and you start with an exponent, whatever inverse you find is going to end up being the opposite kind of problem. Instead of an exponent, the inverse will be a logarithm, or instead of addition, the inverse would be subtraction. Instead of multiplication, an inverse would be division. Okay? So these two equations are inverses. One way that you can check that will be when you graph these functions. If you graph f of x and g of x here, and I recommend that you do that, you will end up with two tables. Okay? One for that top function, one for that bottom function, right? That'll match your graph. Remember, functions have to match graphs, have to match the coordinate points of tables you can come up with. And these tables, notice the x and the y coordinates will be switched. Okay? 0, 2 for one function will be 2, 0 for the inverse. Or 1, 3 for one function's coordinate point will be 3, 1 for an inverse function's coordinate point. So, how can we find the inverse of a function? This is like how you're going to double check yourself. Okay? Once you think you've found the inverse, try to graph the inverse and the original problem you were given. The graphs should have opposite or switched x and y coordinate points. So here's the steps that we're going to do as we're trying to find the inverse of a function. Okay. Let's say that we start with a logarithm, and this is a special logarithm, right? Okay. First thing that we're going to want to do to try to find the inverse is, number one, change f of x to y. They mean the same thing. So this f of x here, we're just going to switch that with a notation that's easier to work with. In this case, that's a y. Okay. Second, we're going to switch the place of x and y. So in this case, all that means is replacing y with an x, replacing x with a y. That's step 2. Step 3, we're going to isolate our logarithm or our exponent. It depends on what we start with. Okay, we start with a logarithm here. We're going to isolate this on one side of our problem first, and then use that to rewrite our problem. So remember your switching formula. We're going to get back to that from last unit. Okay, so in this case, step 3, that 4 is not part of the logarithm. Get rid of it from the right side of the equation. Opposite operations, opposite of negative 4, add 4 to both sides. Now you have x plus 4 equals your natural log of y. This logarithm is now isolated. It's by itself on the right-hand side of the equation. That's the goal, right? Because now we can rewrite this problem. Okay? Remember, the base stays the same. Everything else can switch. If we want to try to rewrite the problem to get y by itself, and we do want to do that, okay, we're isolating y now as part of step 3. So, what's the base here? Well, this is a special logarithm. Remember, it gets a special base. So we're switching from a logarithm to an exponent. In this case, that will be e, is that special base. Okay, e is the special base, and everything else will switch sides, right? Base stays the same, special base for special logarithm. Base stays the same, everything else is going to switch. So this x plus 4 starts on the left side, it's going to move to the right. Y starts on the right side, it's going to move to the left. Okay, you'll get y equals e to the power of x plus 4. Okay. Remember, we switched from a logarithm to an exponent. Those are opposites. When we rewrite our problem, the base stays the same, everything else switches sides. If you start with a logarithm, end up with an exponent. If you start with an exponent, end up with a logarithm. And that's what we've done here. So now you can move on to step 4, which is very simple. Okay. Instead of y, we're going to switch back to function notation, but we're not going to just have f of x. Okay. we don't end up with the same equation, right? We're going to use a little -1 symbol here to tell us that we have found the inverse. This here is the inverse of f of x. Okay? F -1 of x, this is the inverse, is what we're saying. Now you do want to double check yourself, okay? It's always going to be your final step. Don't forget to do this. How do you double check yourself? Remember, graph the original function and graph the inverse. Okay? When you graph them, they should have x and y coordinates that are flipped. So, I don't know, if we had natural log of 1 minus 4, let's say that was 1 comma -3. Maybe it's that, maybe it's not, but let's say it was 1 comma -3. Down here it will be -3 comma 1. The x and y coordinates will switch. That's how you know that this is the inverse of the top function. Okay? So knowing that, knowing these steps, applying them, let's try an error analysis problem and end with this. And for this problem, we're going to start with an exponent, okay, and see what happens when Jeffrey tries to find the inverse of this exponential function. So let's match up our steps, see do they line up. So step 1 here, what did he do? Okay, he switched the place, he changed f of x to y. Okay, this is good. He's correct about this. No mistake yet. Then he switched the place of x and y, right? Y switched with x and vice versa. This is correct as well. Then he added 8 to both sides. He got the base and the exponent by itself, which is correct, right? You do want to get the base and exponent, or the base and logarithm, whichever one you start with, by itself. That's good. And so now he's trying to rewrite his problem. Okay, remember, base stays the same, everything else switches sides. But remember, when you're rewriting your problem, if you start with an exponent, you should end up with a logarithm. When you rewrite, you're rewriting from an exponent to a logarithm, or from a logarithm to an exponent. You never start with an exponent and end up with an exponent. So actually, this step is wrong. Okay, he ends up with another exponent. No, that's not what he should have done here. So this is incorrect. This is his mistake. What should he have done instead? Okay, well, the base does stay the same, but now it will be the base of a logarithm. Right? Log base 3, and everything else is going to switch sides. So y plus 2 will move to the other side of the equation. X plus 8 should move to the other side of the equation as well. So notice in this case, y plus 2 should end up on the left side like this, and x plus 8 should move to the right side of the equation like that. And then finally, you would want to get y by itself. So subtract 2 to both sides to get rid of that on the left-hand side of the equation. And if you write out f -1, remember this is step 4, we're changing out y with our inverse notation. Now we found the inverse. This is what we're saying. We have found the inverse. And the inverse is log base 3 of x plus 8 minus 2 off to the side. Okay. One last thing I'll point out here. Jeffrey is wrong. Yes, he did make this mistake. He did not change his exponent to a logarithm. But notice he stopped at step 4 here. You don't want to do that. Okay, that's why step 5 is so important. If he left that work and thought, oh, I found it, what he could have done was to graph the original function and what he thought was the inverse, and he should have known at that point x and y have not been flipped. This graph's coordinate points will not be the opposite or switched x and y coordinates of the original. This one will. This one does not switch those coordinate points. Okay? That's why step 5 is so important. Double check by graphing. Graph your inverse, graph the original. If they don't have switched x and y coordinates, that's where you can know something's gone wrong and go back through your steps. one at a time, match them up with what we have here. And that's how you can find an inverse. So we've talked about change of base, we talked about inverse. We're going to move into solving in our next lessons, both for exponential and logarithmic equations and functions. And I will see you then.